Hello students, I am Dr. Padmavathi Vedula, AG Patil Institute of Technology, Solapur. This is our 9th lecture. In this lecture, let us see what is Parseval's identity and let us solve some questions on Parseval's identity. So Parseval's identity is very useful in finding some definite integrals. So before seeing that Parseval's identity, let us recall whatever we have discussed in our previous session. In our previous lecture, we have discussed properties of Fourier transform, that is linearity property, change of scale property, shifting property, and modulation theorem, convolution theorem. And we solved some examples. In this session, we are going to discuss Parseval's identity for Fourier transform, and we are going to solve some examples on Parseval's identity. Now, first of all, let us see what is Parseval's identity. Here in Parseval's identity plays around Fourier transform, inverse Fourier transform, and conjugates of Fourier transform and inverse Fourier transform. So here, if we see the statement of Parseval's identity, here we know fx and gx. If fx and gx are some functions, then Fourier transform of fx is f of s, Fourier transform of g of x is g of s. And here fx is inverse Fourier transform of f of s, gx is inverse Fourier transform of capital G of s. Then, here according to Parseval's identity, 1 by 2 pi integral minus infinity to infinity, here Fourier transform f of s into conjugate of the Fourier transform of g of s ds equal to integral minus infinity to infinity fx and conjugate of gx dx. Here, you know conjugate of a complex number. Here if z equal to x plus iy is a complex number, then conjugate of this complex number is z bar equal to x minus iy. In the same manner, here Fourier transform is involves these complex variables. So here capital F of s, capital G bar s is nothing but conjugate of this G of s, and Gx is conjugate of G bar x is conjugate of G of x. Now if we see next statement of Parseval's identity, 1 by 2 pi integral minus infinity to infinity, here Fourier transform square modulus of Fourier transform square ds equal to integral minus infinity to infinity mod of fx square dx. This is inverse Fourier transform. Here where g bar x is complex conjugate of g of x. Here g bar x means this one conjugate of this function g of x. If this g of x contains some complex variables, if we change sign of that complex part, that is imaginary part, then we get conjugate of this function g bar x, g of x. Now, let us see proof of these statements. Here we know Fourier transform, formula of Fourier transform and formula of inverse Fourier transform. Here this fx means inverse Fourier transform fx equal to 1 by 2 pi integral minus infinity to infinity f of s e power minus is x ds. Now, if we see definition of Fourier transform, so f of s, Fourier transform f of s equal to integral minus infinity to infinity fx into e power is x dx. Now gx equal to 1 by 2 pi integral minus infinity to infinity. Here Fourier transform of gx is capital G of s into e power minus is x ds. If we see definition of Fourier transform capital G of s equal to integral minus infinity to infinity g of x e power is x dx. Now, let us see conjugate of this inverse Fourier transform of gx, that is g bar x equal to 1 by 2 pi integral minus infinity to infinity. Here conjugate of this transform g of s into e power is x ds. So whenever you are finding conjugate of g of x, even this in this integrand, whatever the Fourier transform may be there in that place, we should take conjugate of that Fourier transform. Now here this conjugate of Fourier transform g bar s equal to integral minus infinity to infinity small g bar x e power minus is x dx. Now, let us see this first statement, integral minus infinity to infinity fx into g bar x dx, which is equal to, according to definition of this g bar x, this can be written as integral minus infinity to fx into, here in the place of g bar x, let us write this one, 1 by 2 pi, here 1 by 2 pi integral minus infinity to infinity g bar x e power is x ds dx. So, in the place of g bar x, we have written this one, RHS of g bar x. Now, here, if we change order of this integration, here this is double integration, if we change order of this integration, this g bar s can be written outside. So, g bar x into integral minus infinity to infinity fx into e power is x dx ds. Now, this is equal to 1 by 2 pi integral minus infinity to infinity g bar s into the terms which are in the bracket is nothing but Fourier transform f of s. So, in the place of integral minus infinity to infinity fx e power is x dx, we can write f of s, Fourier transform f of s. So, here f of s ds. Let us consider this function g of x equal to f of x. Then, integral minus infinity to infinity fx into f bar x dx means in this statement, in this LHS, we have replaced this g bar x conjugate of g of x by conjugate of f of x, because we have taken g of x equal to f of x. Then here integral minus infinity to infinity fx into f bar x dx equal to, according to this statement 1, here we get 1 by 2 pi integral minus infinity to infinity conjugate of f of s into f of s ds. Now, we know here conjugate into that function gives modulus of that function square, because we know z into z bar conjugate z into conjugate of z equal to mod z square. So, according to this definition, we can apply that for functions also. So, here integral minus infinity to infinity fx into f bar x gives mod fx square dx, which is equal to 1 by 2 pi integral minus infinity to infinity mod f of s square ds. This is nothing but second statement of Parseval's identity. Now, here Parseval's identity, we can define Parseval's identity for cosine and sine transforms also. So, for cosine transform, here 2 by pi integral 0 to infinity cosine transform of s and cosine transform of g of x, that is gc of s ds equal to integral 0 to infinity fx into gx dx. Now, 2 by pi integral 0 to infinity fs of s sine transform, here gs of s, this is sine transform of g of x ds equal to integral 0 to infinity fx into gx dx. So, if you observe here, both RHS are same, but on LHS, here in this first statement we have taken cosine transforms, and in this second statement we have taken sine transforms. Now, in this third statement, if you see, this is on left hand side, 2 by pi integral 0 to infinity cosine transform modulus of cosine transform square ds equal to integral 0 to infinity fx square dx. Now, 2 by pi integral 0 to infinity modulus of sine transform square ds equal to integral 0 to infinity fx square dx. Even in these last two statements, RHS is same, but LHS are different. Now, Parseval's identity is useful to evaluate some definite integrals. So, let us see working method first. Working method to evaluate integrals using Parseval's identity. So, in first step, if fs Fourier transform and inverse Fourier transform, if both are given in the question, then directly we can apply Parseval's identity to evaluate the integral whatever is asked. But if fx is provided and if it is asked to find Fourier transform, then evaluate any particular integral, then using definition of or formula of Fourier transform, first we have to find f of s, then we apply Parseval's identity to evaluate the integral. But in some questions, they provide only the integral which is to be evaluated. They don't provide this function fx or Fourier transform f of s. Then according to that integrand, that means we have to check whether integrand is fx or fx into gx or in the form of f of s Fourier transform or product of two Fourier transforms f of s into g of s. Then here I have provided one table in the next slide. So from that table we have to choose the required transform, that is Fourier. If Fourier transform is provided, we have to choose the function. If this function fx or inverse Fourier transform is provided, so according to that we have to choose Fourier transform. Now here choose respective required expression from the table. That means if fx is given, then take f of s or cosine transform or sine transform according to given integrand in the integral. Here then we apply relevant Parseval's identity to evaluate the integral. So here if only integral is provided, then integrand is in the form of some e power minus x square, then you have to choose cosine transform root pi by 2 into e power minus s square by 4. In some questions you may evaluate integral some 0 to infinity a by s square plus a square ds something, then you have to choose fx equal to e power minus ax. So you will understand how do we take this function and how can we evaluate this and all while solving examples. Now let us see some examples. Here I have listed some 8 examples. So let us solve one by one. So first one is, see, you can change variation of these questions. Here in first question fx is provided and Fourier transform also provided, then prove that integral 0 to infinity sine square ax by x square dx equal to pi a by 2. That means both fx and fs are provided in question number 1. But in question number 2, only function fx is provided, fs is not provided. And here in question number 3, both fx and fs not provided. Directly they asked to evaluate this integral. Okay, so in this first case, no need to choose any fx or fs from the table. But in the second case, here only function is provided. Then here also only function is provided, but Fourier transform we can find using formula of Fourier transform. So no need to choose any function from the table. But in this third question, third, fourth and fifth questions, here we have only this integral. This integral is containing 1 minus cos x by x whole square dx. So we have to check that table. In that table, wherever you find 1 minus cos x by x term, then according to that you have to choose other transform. Okay, let us see that while solving questions. Now, let us see first question. Here I have listed 8 questions. So I think we can solve only 4 questions in this session. So let us see. So first one is, first question is, if fx equal to, if fx equal to 1 mod x less than a, 0 for mod x greater than a, and Fourier transform of this function is 2 sine sa upon s, prove that 2 sine sa upon s, prove that integral 0 to infinity sine square a x upon x square dx equal to pi a upon 2. Okay, so first let us write given information first. So here what is given? Function is given, fx equal to 1 for mod x is less than a, 0 for mod x is greater than a. And Fourier transform of this function is Fs equal to 2 sin Sa upon S. Now, here there are so many formulae of Parseval's identity. That means there are two formulae on Fourier transform, there are two formulae on cosine transform, and there are two formulae on sine transform. So among those, here how do you choose the identity which is to be taken to solve this question? So here, to decide that, observe this integrand. Here integrand is in the form of squares, sin square ax upon x square dx. So choose the identity which is having squares and Fourier transform. So if we choose Parseval's identity of Fourier transform which is having square, so here Parseval's identity is 1 by 2 pi integral minus infinity to infinity Fourier transform mod Fourier transform square ds equal to integral minus infinity to infinity fx square dx. Okay. Now here we know fs also we know, even fx we know. So let us write those here. So here 1 by 2 pi integral minus infinity to infinity 2 sin Sa upon S whole square ds equal to integral minus infinity to infinity. But here in this function, if you observe, limits are fx equal to 1 for mod x less than a, that means minus a less than x less than a, and this function is 0 for minus infinity less than x less than minus a, and a is less than x less than infinity. So here on right hand side we can split this integral into three integrals: minus infinity to minus a fx whole square dx plus integral minus a to a fx whole square dx plus integral a to infinity fx whole square dx. So in this first integral, this function is 0 because in first and last integrals minus infinity to minus a, and in the interval a to infinity this function is 0. So here on right hand side we get minus a to a fx whole square dx. But what is fx here? Fx is 1 in this interval. So here 1 dx. Okay, here fx is 0, here fx is 1. Again here fx is 0. So here we get 1 by 2 pi integral minus infinity to infinity, here 4 sin square Sa upon S square ds equal to integral minus a to a dx. Okay, so let us evaluate this. Here don't write equal to sign here. Now 1 by 2 pi, if you take 4 outside, 4 by 2 pi integral minus infinity to infinity sin square Sa upon S square ds equal to, on the right hand side, integral minus a to a dx. So integral dx is x under the limits minus a to a. Then here you get, if you apply limits, a minus of minus a, which is equal to a plus a, that is 2a. So integral minus infinity to infinity sin square Sa upon S square ds equal to 2a into, here if you cancel this, you get 2 by pi, here pi by 2. Okay, then you get, which is equal to pi a. This 2 and 2 will get cancelled, you get pi a. But here on left hand side, this is even function. Sine is odd function, but sine square is even function. So we can write it as 2 integral 0 to infinity. Here sine square SA upon S square ds equal to pi into a. Because we know integral minus a to a fx dx equal to 2 integral 0 to a fx dx if fx is even. So here sine square function is even function. So we can write this as 2 integral 0 to infinity sine square SA by S square ds. So integral 0 to infinity sine square SA upon S square ds equal to pi a by 2. To get the required proof, put s equal to x. If we put s equal to x, then we get integral 0 to infinity sine square ax upon x square dx equal to pi a by 2, which is required proof. Now let us see next question. Next question is, here in this question function is provided. We have to find Fourier transform as well as we have to evaluate our integral. So here find Fourier transform of fx equal to 1 minus mod x when mod x is less than 1, 0 when mod x is greater than 1. Hence show that integral 0 to infinity sine power 4t upon t power 4 dt equal to pi by 3. So here first we have to find Fourier transform f of s. After finding f of s, using Parseval's identity, we can evaluate this integral. So first let us write a given function, then let us write formula of Fourier transform. So given function is fx equal to 1 minus mod x when mod x is less than 1 and 0 when mod x is greater than 1. Now let us write Fourier transform. Here what is it mean? Mod x is less than 1 means minus 1 less than x less than 1. Here this means minus infinity less than x less than minus 1 and 1 is less than x less than infinity. That means here x is in the interval minus infinity to minus 1 or 1 to infinity. But in both these intervals value of this function is 0 and in the interval minus 1 to 1 value of fx is 1 minus mod x. Now let us write formula of Fourier transform. So Fourier transform f of s equal to integral minus infinity to infinity fx into e power isx dx. Okay. isx dx plus integral minus 1 to 1 fx e power isx dx plus integral 1 to infinity fx e power isx dx. Now in the interval minus 1 to minus 1 fx is 0. Again in the interval 1 to infinity fx is 0. But in the interval minus 1 to 1 fx is 1 minus mod x. So we can write this integral as integral minus 1 to 1 fx e power isx dx. Now let us write e power isx equal to e power is x equal to cos sx plus I sin sx. According to the formula, I e power I theta equal to cos theta plus I sin theta. Again, that integral can be written as integral minus 1 to 1. So, in the interval minus 1 to 1, fx equal to 1 minus mod x. So, 1 minus mod x into, in the place of e power I sx, we can write cos sx plus I sin sx dx. Now, here this is nothing but integral minus 1 to 1, 1 minus mod x into cos sx dx plus integral minus 1 to 1, 1 minus mod x into I sin sx dx. Here cos sx is even function and sin sx is odd function. So this first integral can be written as 2 integral 0 to 1, 1 minus mod x into cos sx dx, and this second integral is 0 according to the formula of definite integration. Since integral minus a to a fx dx, we know this, we have already used so many times. Integral minus a to a fx dx equal to, here 2 integral 0 to a fx dx, if fx is even, fx dx, if fx is even, which is 0 if fx is odd. So, by using this definite integration formula, this value of second integral is 0. Now, in the interval 0 to 1, mod x is plus x only. So, we can write it as 2 integral 0 to 1, 1 minus x into cos sx dx. Now, we have to evaluate this integral. To evaluate this integral, we use integral uv rule. So, integral uv equal to uv dash minus u1v double dash plus u2v triple dash minus so on. Here 1 minus x, consider 1 minus x as u and cos sx as v. Now, here u1, u2, u3 so on are derivatives of u and v dash, v double dash, v triple dash are integrals of v. Here let us consider u equal to 1 minus x. Then u1 is d by dx of 1 minus x, which is minus 1. u2 equal to, u2 is nothing but d by dx of minus 1, which is equal to 0. Now let us consider v. Here v equal to cos sx and v dash equal to integral cos sx dx, which is equal to sin sx upon s. V double dash equal to integral of sin sx upon s dx, which is equal to minus cos sx upon s square. So let us substitute all these values in this uv rule to evaluate the integral. Then we get 2 integral 0 to 1, 1 minus x into cos sx dx equal to 2 into here 1 minus x into u into v dash. V dash is sin sx upon s minus u1. u1 means derivative of u, that is minus 1 into integral of sin sx upon s, that is minus cos sx upon s square under the limits 0 to 1. That is 2 into 1 minus x into sin sx upon s. Here there are 3 negative signs. So, product of those 3 negative signs gives a negative sign. So, here minus of cos sx upon s square under the limits 0 to 1. Now, if we apply limits, apply first upper limit, that means put x equal to 1. So, we get 1 minus 1 into sin s upon s minus cos s upon s square. So, whenever you are applying lower limit, signs of these terms they will change. So, here minus of 1 minus 0 into sin 0 upon s plus cos 0 upon s square. That is 2 into here first term becomes 0 minus cos s by s square Here again minus 0 because sin 0 is 0 and cos 0 is 1. Cos 0 equal to 1. So if we use these values here, third term becomes 0 and fourth term becomes 1 by s square. So which gives 2 into 1 minus cos s upon s square. This is Fourier transform. Fs equal to 2 into 1 minus cos s upon s square. Okay. Now we have to apply Parseval's identity to evaluate the integral. To choose Parseval's identity, because there are so many forms in Parseval's identity, so to choose that form, first observe given integral which is to be evaluated. So in that integral you can observe square terms, sine square terms. That's why here we consider the Parseval's identity which is having square terms. So here Parseval's identity is 1 by 2 pi integral minus infinity to infinity mod of Fourier transform Fs square ds equal to Fx square dx. Integral minus infinity to infinity Fx square dx. Now here Fs is this one. So let us write this again. That is 1 by 2 pi integral minus infinity to infinity 2 into 1 minus cos s upon s square whole square ds equal to, here this integral can be written as minus infinity to minus 1 fx whole square dx plus integral minus 1 to 1 fx whole square dx plus integral 1 to infinity fx whole square dx. So in this first interval and last interval this function is 0, in the middle interval it is 1 minus mod x. So we can write it as integral minus 1 to 1 minus mod x whole square dx. Here 1 minus mod x whole square is even function, so we can write it as 2 integral 0 to 1 minus x whole square dx. So if we evaluate this integral, you get 2 into 1 minus x whole cube by 3 into d by dx of 1 minus x under the limits 0 to 1. That is 2 into 1 minus x whole cube by, here 3 into minus 1. Derivative of 1 minus x is minus 1 under the limits 0 to 1. That is here 2 by 3. Okay, minus 2 by 3 into 1 minus x whole cube under the limits 0 to 1. So here minus 2 by 3 into, if you apply upper limit, this becomes 0, 1 minus 1 0, minus 1, which is equal to 2 by 3. So here we can write it as 1 by 2 pi integral minus infinity to infinity 4 into 1 minus cos s whole square upon s power 4 ds equal to 2 by 3. So integral minus infinity to infinity, here this 4 you can take outside, 4 by 2 pi, here 1 minus cos s whole square upon s power 4 ds equal to 2 by 3. So integral minus infinity to infinity 1 minus cos s whole square upon s power 4 ds equal to 2 by 3 into 2 pi by 4, which is equal to pi by 3. Now here 1 minus cos s, 1 minus cos theta equal to 2 sin square theta by 2. So we can write it as integral minus infinity to infinity, integral minus infinity to infinity, here 2 sin square s by 2 whole square upon s power 4 ds equal to pi by 3. That is integral minus infinity to infinity 4 into sin power 4 s by 2 upon s power 4 ds equal to pi by 3. Now this s power 4 here multiply and add 2 power 4 because here s by 2 is there. So to bring s by 2 in the denominator, we have to multiply and divide this s power 4 by 2 power 4. So let us see here integral minus infinity to infinity, integral minus infinity to infinity 4 into s power 4 sine power 4 s by 2 upon 2 power 4 into s power 4 by 2 power 4 ds equal to pi by 3. So we can write it as integral minus infinity to infinity 4 into sine power 4 s by 2 upon 2 power 4 into s by 2 raised to 4 ds equal to pi by 3. Now here we can convert this integral in terms of other variable by choosing s by 2 equal to t. So let s by 2 equal to t. So ds equal to 2 into dt. When s equal to plus infinity implies t equal to plus infinity. When s equal to minus infinity implies t equal to minus infinity. So this can be written as integral minus infinity to plus infinity. Here 4 by 2 power 4 means here this is 2 square. So here sine power 4t upon 4t power 4 into 2 dt equal to pi by 3. Okay, so this is nothing but integral minus infinity to infinity 1 by 2 into integral minus infinity to infinity sine power 4t upon t power 4 dt. Here because you can cancel these two numbers equal to pi by 3. Here sine power 4 is even function. So again this can be written as 1 by 2 into 2 integral 0 to infinity sine power 4t by t power 4 dt equal to pi by 3. Here this 1 by 2 and here 2 will get cancelled. We get implies integral 0 to infinity sine power 4t upon integral 0 to infinity sine power 4t upon t power 4 dt equal to pi by 3. So this is required result because we have to evaluate the integral 0 to infinity sine power 4t upon t power 4 dt which is equal to pi by 3. Now let us see next question. Third question is evaluate integral 0 to infinity sine square x by x square dx. Here function is not provided and Fourier transform is also not provided. We have to evaluate this integral. So as we discussed, whenever function fx, that means whenever Fourier transform as well as inverse Fourier transform are not provided, then we have to consider this integrand as one of those two and we have to choose the other one from the table. So here see this table. In this table, in this term, if you put a equal to 1 here, if you put a equal to 1, you get and s equal to x, we get sine x by x. Okay, then here this interval becomes 0 less than or equal to x less than or equal to 1. Here this becomes 1 is less than or equal to x less than or equal to infinity. So whenever you find 1 minus cos x by x or sin x by x, such type of terms in the integrand, then choose fx equal to 1 0. So according to this table, according to that table, we can consider fx as let fx equal to 1 when 0 less than or equal to x less than or equal to 1, 0 for x is greater than 1. Consider this function. Now, if function is this, then its Fourier cosine transform fc of s equal to sin s by s. Sin s by s. We can find it here. After choosing this function, by applying cosine transform formula, we can find that cosine transform. Here function is fx equal to 1 in the interval 0 to 1 and 0 for x is greater than 1. Now let us check Fourier cosine transform for this function. So we can find Fourier cosine transform using the formula integral 0 to infinity fx cos sx dx. So this is equal to integral 0 to 1 fx cos sx dx plus integral 1 to infinity fx cos sx dx. In the interval 1 to infinity, value of the function is 0. In the interval 0 to 1, value of the function is 1. So here we get integral 0 to 1 cos sx dx. If you evaluate this, sin sx upon s under the limits 0 to 1, which is equal to sin s by s minus sin 0 by s, which is equal to sin s upon s, which is equal to sin s by s. What is this? This is Fourier cosine transform. After getting Fourier cosine transform fc of s and this fx, we have to apply Parseval's identity. Here integrand contains squares, so we use the Parseval's identity which is having squares. So here Parseval's identity for Fourier cosine transform, identity for Fourier cosine transform is Fourier cosine transform is 2 by pi integral 0 to infinity fc of s square ds equal to integral 0 to infinity fx square dx. Okay, now here this is fc of s, this one is fc of s, Fourier cosine transform, and here fx means this one is fx. So if you replace those values, you get 2 by pi integral 0 to infinity 2 by pi integral 0 to infinity sin s by s whole square sin s by s whole square ds equal to integral 0 to infinity fx dx. But here interval is divided into two intervals, 0 to 1 and 1 to infinity. So we can write this 0 to infinity as 0 to 1 fx square dx plus integral 1 to infinity fx square dx. In the interval 0 to 1, here fx equal to 1 dx plus integral 1 to infinity 0 dx, which is equal to x under the limits 0 to 1, which is equal to 1. So here 2 by pi integral 0 to infinity sin square s by s square ds equal to 1 implies integral 0 to infinity sin square s by s square ds equal to pi by 2. If you put s equal to x, then we get integral 0 to infinity sin square x by x square dx equal to pi by 2, which is required solution. Now let us see next question, fourth question. So here fourth question is evaluate integral 0 to infinity dt by t square plus 1 whole square equal to pi by 4. So here not evaluate, show that because RHS is also given. So here show that integral 0 to infinity dt by t square plus 1 whole square equal to pi by 4. Now here also we have to choose the function. Function is not given. So from this table you can choose the function. So here if you observe, that is 1 by t square plus 1 whole square. So here if you put a equal to 1, then you get 1 by t square plus 1. Here if you put a equal to 1, here you get and s equal to t, you get 1 by t square plus 1. Right. So here if you put a equal to 1, then the function becomes e power minus x. Okay. So we are having this one 1 by t square plus 1 form. So you have to choose fx equal to e power minus x. So here if you choose that function, let us see solution. So here let fx equal to e power minus x. We have seen for the function fx equal to e power minus x, Fourier cosine transform fc of s equal to 1 by s square plus 1. Now, let us use Parseval's identity of Fourier cosine transform. So, here Parseval's identity for Fourier cosine transform. For Fourier cosine transform is 2 by pi integral 0 to infinity fc of s whole square ds equal to integral 0 to infinity fx whole square dx. Now let us use these fc of s and fx here in this Parseval's identity. Then we get 2 by pi integral 0 to infinity 1 by s square plus 1 whole square ds equal to integral 0 to infinity e power minus x whole square dx. So here this is 2 by pi integral 0 to infinity 1 by s square plus 1 whole square ds equal to integral 0 to infinity e power minus 2x dx. Let us evaluate this integral which is on the right hand side, because we have to evaluate this integral, left side integral. So let us simplify RHS. So integration of this is e power minus 2x upon minus 2 under the limits 0 to infinity. If we apply upper limit, value of this term is 0. When you apply lower limit, you get e power 0 by minus 2. But value of e power 0 is 1. So here we get 1 by 2. Okay. That means on the left hand side, we are having 2 by pi integral 0 to infinity 1 by s square plus 1 whole square ds, and on the right hand side we have obtained 1 by 2. Now let us transfer this 2 by pi to right hand side. Then we get integral 0 to infinity 1 by s square plus 1 whole square ds equal to 1 by 2 into pi by 2, which is equal to pi by 4. Now put s equal to t. Change this variable s to t. So here integral 0 to infinity 1 by t square plus 1 whole square dt equal to pi by 4. This is solution of this question. Let us see some more questions on Parseval's identity in our next session. Thank you.